Hi everyone, Mr. Lee here. In this video, we're going to go over impulse and momentum. All right, let's get started. So I'm going to first start off with this idea called momentum. Now, believe it or not, we use the word momentum in our day-to-day language, right? Like in sports, we say that a team has this momentum, or anytime there's voting that happens, like, oh, this person is unstoppable. They have great momentum. So that is the everyday language that we use for momentum, and the physics definition actually comes pretty close. The idea behind momentum or a object with momentum is like you gotta imagine they're like hard to stop. But like when you're imagining an object with momentum, that object is usually moving. And believe it or not, that is the equation for momentum. And we covered this back when we talked about Newton's laws. We said that the first law stated that an object in motion, it stays in motion. And that right there is the definition of momentum. If we have an object that is moving, that object is said to have momentum. Now the variable for momentum, it would make sense that it was a m, right? Because m for momentum, but we already have m for mass. And so instead what we use is the letter p, because that makes so much sense. P for momentum. All right, now you might be thinking to yourself, well, why is the variable for momentum p? Now, I don't know how true this is, but I was always taught that back in the good old days, right around when Isaac Newton was around, they spelled momentum with the P, and the P was silent. And that just confused way too many students, so they just took out the P. But the variable for momentum P, it stayed around. That is 100% not true, but now you'll know that the variable for momentum is P. So with the units with the variable momentum as P, we can also figure out the units. We know that the units for mass is kilograms, and the units for velocity is meters per second. And so the units for momentum is kilograms meters per second. Or, and here's a new one, we can actually change this into Newton seconds. Okay, so both of these are the proper units. There is no one unit for momentum, but both of those, it works out. Okay? So the big idea here is that if you have an object that is moving, we say that the object has momentum. That is the definition for momentum. Now, if we were to take a look at the other side, which is impulse, we can actually go back to Isaac Newton's first law. He said that an object in motion, it stays in motion unless there is a outside force, right? So this right here, an object in motion, it stays in motion unless there's an outside force. This is what we call the law of conservation of momentum, and we'll get more into it later. But with this idea, we can actually come up with the definition for impulse. Okay? So he said an object in motion, it stays in motion unless there is an outside force. Okay? And now we're going to be talking about systems here. We talked about systems when we were talking about energy, the system's energy, right? The total amount. And we say that the system's energy, it can never change unless there's an outside force, and that's because work is done. The same idea is true for momentum. A system's momentum, an object in motion stays in motion unless there's an outside force. A system's momentum can never change unless there's an outside net force that causes a change in momentum. And that cause for a change in momentum by a force is what we call impulse. So simply put, if you have a force that is acting on an object over a period of time, the object will have a change in momentum. Okay? So we can actually, before we do that, the variable for momentum, you would think it's a capital I, but it's not. It's actually a capital J. J for impulse. And this is because back in Isaac Newton's days, there used to be a J in front of the word impulse, but the J was silent, and that just really confused a lot of people because they started calling it Jimpulse, and so they're like, you know what, let's just get rid of it, no J, but the variable for impulse, which is J, it stuck around. Okay? So we have this giant equation here. We say that the impulse for a system is determinate if there's a force, an outside net force acting on the system over a period of time. Okay, so if you have a force acting on a system, the system will have a change in momentum. So we can actually expand this out a little bit because we know that delta is the final momentum minus the initial momentum. So we can write out the equation like so. And so if we were to take a look at this version of impulse, we can see why the units for momentum, Newton seconds, exist. Because the units for force is a Newton, and the units for time are seconds. And so the impulse, the units for impulse is a Newton second, and impulse is simply the change in momentum. So I'm going to highlight this line right here. Okay? All right. Now, how does this affect us, right? This affects us because this actually describes a lot of what happens in our lives. If you have a moving object, the only reason why that object ever slows down or speeds up is because there are outside forces. That is impulse. If there's an outside force, it affects the motion. And later on, we're going to describe how different objects within the system, how they can interact with each other, and how they can affect the impulse of a system. And this is what we call collisions. So we're going to, during this unit, we're going to take a look at how objects colliding interact with each other. Okay, and this has everyday applications such as the safety of your car, and if you play sports, it has everything to do with collisions. That's all about impulse and momentum. Okay, so before I end the video, one thing that we always look into when we do these equation introductions is how will the graph be represented. Okay, so I'm going to take a look at the equation for impulse. So J is equal to force times delta time. And if we were to take a look at this equation, we can see that if you have the two variables that are multiplied together, this is what we call the area under the curve model. So for example, if we have force times time, okay, with time being seconds and force being newtons, and let's say we have, I don't know, a variable force like this. This is section 1, and we have something like this. This is section 2, and we have something like this. This is section 3. Okay, I'm going to shade in the area under the curve for each part. So this is part 1, this is part 2, and this is part 3. So because this is a force times time graph, we can see that the area under the curve, so for section 1, it'll be 1/2 base times height, and our base is just the time, and the height is the force. Okay, that can give us the change in momentum. And this is extremely helpful if you know the object's initial momentum, because we know that the change in momentum is always going to be the final momentum minus the initial momentum. And this area under the curve, this gives us, this is the big major point here, this gives us the change in momentum. Whatever the area under the curve is, that is the change in momentum. And we can say that is the impulse. Same for area number 2. So in the area number 2, we have this giant rectangle, right? So whatever the area is of that rectangle, that tells us the change in momentum. Okay? And same for number 3. 3 will tell us the change in momentum for whatever that is. And if you wanted to find the total change in momentum, you would just add up the area under the curve for parts 1, parts 2, and parts 3, and then we can find the total area under the curve, okay, and which is your total impulse. All right. The last thing I want to cover is how we came about with this idea of momentum from Isaac Newton. Now, believe it or not, Isaac Newton's equation, his famous one, F equals ma, he actually wrote this in terms of momentum first. So before we sign off, I want to break this one down. We know that this is his famous second law, but he actually didn't write it like that. He wrote something more like this. So we know that acceleration is the change in velocity over the change in time. Okay? And so right here, you should be able to see our newly discovered equation. So this was the form of the equation that he wrote, but with a little modification. So what I'm going to do is I'm going to multiply both sides by delta t. And the reason I want to do that is just so that you can see something mathematically. So I'm going to cancel out the denominators there. So we get force times the change in time is equal to mass times the change in velocity. Okay, so this right here, we discovered that this is impulse. right? Force times change in time is impulse. And we know that impulse is the change in momentum. So if we take a look here, on the left-hand side, or on the right-hand side of the equation, we see mass times the change in velocity. And we know that change in velocity is v final minus v initial. And if I distribute out the mass, we get mass times v final minus mass times v initial. And so from Newton's second law, we get the impulse equation. And that is how Isaac Newton described the second law when we first started off. He said that it was the impulse, or the outside force acting on a system, would change the object's momentum. And that's how the first law came about as well. An object in motion stays in motion, an object at rest stays at rest. All right, so that was a nice little history lesson. That's it for the introduction to the impulse and momentum equation. Let's do a quick recap. The equation for momentum is mass times velocity. Okay, any object or any system that is moving has momentum. We learned that impulse is the change in momentum, and the only way that a system's momentum can change is if there's an outside force. And we also discovered how we can go from Newton's second law to the impulse equation. Next time, we're going to go over the conservation of momentum, the different kinds of collisions, and we will wrap this up. I'll see you then. Bye-bye.